My name is Thomas Salper, and we are looking at part two of our case study for the Lockheed-Martin C-130 Hercules aircraft and what it is required in terms of engine power in order for it to take off in a fully loaded condition. But let's briefly review part one, where we saw for the aircraft loaded with 150,000 pound force, it required of the order of 4,200 pound force of thrust to maintain constant altitude and constant velocity while flying at 20,000 feet elevation for 1,500 miles at a speed of 350 miles per hour. We saw that 2,000 horsepower of shaft power were required by each engine to maintain steady flight at constant elevation. Now we're going to up the game and see what engine size would be required for it to take off with 175,000 pound force of total weight in using a runway of length 3,750 feet. So this increases the amount of power required by the engines, and we're going to see if that comes in closer agreement with the total horsepower, shaft horsepower needed by the engines. So you can see these aircraft are intended to carry very heavy vehicles, such as the Army tank being loaded right there. And you can see on the interior, there's quite a bit of weight held by that airframe, in addition to personnel and fuel that can bring it up to of the order of 175,000 pounds for dropping off cargo at whatever location may be needed. So the extremes of carrying load for this aircraft are 175,000 pounds for wartime conditions. Now let's do a quick look again at the typical dimensions of the aircraft. So we've got 133 feet of wingspan, about 100 feet of length, about 40 feet of height, and then the planform area of 1,745 feet. We'll disregard the empty weight, the useful load, and the takeoff weight, which we know is now 175,000 pounds. And let's briefly refresh on the answer that we're kind of expecting to see, about 4,600 shaft horsepower of power for each of the turboprop engines, which are turbines with propellers attached to them, which have a diameter of 13.5 feet. So if we look at our NACA 64A318 airfoils, we can see that an angle of attack of 6 degrees, the lift coefficient is about 1.07, and the corresponding drag coefficient is about 0.014. But if we were to find the takeoff speed required for this aircraft, we'd see it would be inordinately high to attain sufficient lift force given this relatively low lift coefficient, which is sufficient for level horizontal flight, as we saw in the case study part one. But for takeoff, we need a little more of a lift coefficient, and evidently someone, last name Fowler, perhaps worked at Lockheed-Martin, developed what's referred to as a high lift flap needed for the aircraft, the airfoil itself, our NACA 64A318, to provide sufficient lift force for this aircraft to take off on a relatively short runway under fully loaded conditions. So here's an example, cutaway, cross-sectional view of a Fowler flap. And you can see there's also a slat and Fowler flap right there that gives a higher lift coefficient. But we're going to go with this lift coefficient of 2.8, a substantial improvement over the 1.07 lift coefficient that it can get without any movable components. You can see this wing flap on the back right here performs an aerodynamic phenomenon that enhances lift substantially. So let's look at our new delivery deliverables for case study 2. We're given a fully loaded C-130 aircraft using the NACA 64A318 airfoils, takes off in calm air. That is to say, the wind speed is 0 feet per second or miles per hour in this case, and it's got a runway length of 3,750 feet. This is a relatively short airfield, and it's kind of typical of some of the extreme conditions that these aircraft can be pushed to under wartime conditions. As I mentioned, we're going with 175,000 pound force of total weight in all conditions of these calculations. Propeller diameter is the same. We've got a air density typical of sea level. So the elevation here we'll just say is around 0, maybe 100 feet or so. We don't know what the takeoff velocity is. In fact, that's one of the deliverables for our calculations here. We see it's at sea level. The wingspan, planform area, and frontal area remain the same as the first instance. We've got our lift coefficient of 2.8. We've got a somewhat higher drag coefficient of 0.03. And our fuselage drag coefficient remains the 0.02 we saw earlier. And then the propeller efficiency and engine efficiency remain those conservative values that we saw for case study part 1, just to ensure that our engines are sized adequately for the extreme condition. And again, we'll be using JP8 fuel with its energy content of 135,000 British thermal units per gallon. So our first calculation is determine the required takeoff velocity using the lift coefficient shown there. Then find the required acceleration under these conditions, the required takeoff time. Then we'll use summation of forces in the x direction to determine our required wing drag force, fuselage drag force, and thrust force for the aircraft to be able to actually lift off the ground. Beyond that, we'll look at our propeller air velocity and our total mass flow rate, as well as our propeller shaft power and the total fuel required for the aircraft to take off. That is to say, the fuel used in 3,750 feet of acceleration, I'll say constant acceleration, from our initial position to liftoff. So let's start with a review of the velocities that we see. So on the one hand, we know that the airframe or the aircraft induces a velocity over itself based on the speed of the aircraft. So we start with just kind of a look at how it is that gives rise to the lift force. The airframe speed and the induced velocity is used to produce the lift force with the lift coefficient of 2.8 that we saw earlier, acting on the planform area of 1745 square feet. So we need to find the velocity of the aircraft at takeoff, which remains unknown for the present time, knowing that the lift force has to be greater than or equal to, we'll say slightly greater than, the total weight of the aircraft, which was the 175,000 pounds that we saw. Beyond that, we know that we need to use summation of forces in the x and y direction to figure out all parameters of this takeoff condition, and we also need to use the conservation of linear momentum equation, an adaptation of Newton's second law, in order to figure out the thrust force acting on the aircraft. And we'll go with the simplified representation right here, where we treat our momentum flux correction factors beta as equal to 1 for this steady turbulent flow over the aircraft. And we also know that this thrust force here has to be greater than the total drag force acting on the wing and the drag force acting on the fuselage to provide sufficient acceleration to bring this aircraft up to the takeoff velocity required by the aircraft. So let's start with just kind of a summation of forces in the y direction. So summation of forces in the y direction is equal to the acceleration in the y direction, which we're going to say is just above 0 because it doesn't have to accelerate very quickly upward, but it does have to go upward, of course, to clear any obstacles that may be further down the runway, as long as it takes off in that 3,750 feet of runway distance. So let's start with the force equations in the y direction. We've got summation of forces in the y direction are equal to force of lift minus minus the total weight of the aircraft is equal to mass times acceleration in the y direction, and we saw that that's sufficient that be a quite low value. It just has to start accelerating upward, but it doesn't require the same as the higher horizontal acceleration that's required. So we'll say this is equal to 0 such that force of lift is equal to the total weight of the aircraft. And then using our lift calculation, we've got lift coefficient maximum, the 2.8 that we saw earlier, times 1/2 density, velocity, and I'll use velocity 1 squared. So this is the velocity of our aircraft at takeoff times the planform area of the aircraft. Now remember, this is lift coefficient. This is dynamic pressure multiplied by area gives us a dynamic pressure force. Now we can solve that upper right equation to find our V1 is equal to the square root of 2 times the weight, the total weight of the aircraft, divided by the density, times the lift coefficient, which is set to a maximum using the Fowler flaps, times the planform area. So plugging in values here then, we can say our takeoff velocity, V1, or V final for the acceleration along the runway, is equal to 2 times 175,000 pound force divided by 0.0777 pound mass per cubic foot times our lift coefficient of 2.8 under the maximum conditions times our 1745 square feet of planform area. Now you may notice that we need to ensure that our units cancel properly such that we have the square root of units of feet squared per second squared to give us a velocity of feet per second squared. So we need to multiply by the unity conversion ratio, 32.2 pound mass feet per second squared, and this gives us our velocity V1 of 172.3 feet per second as V1. Box the answer. It's the first of 10 that we're looking for in this set of calculations. Now let's jump forward to what's really a return to your dynamics class to understand the acceleration and time needed for this aircraft to take off. So on the one hand, we just calculated that the aircraft needs to be moving at 172.3 feet per second, and we could say this is the velocity of the aircraft relative to the ground. If you were an observer at a distance, you could see that aircraft moving at 172.3 feet per second before it actually takes off from the ground, before the lift force equalizes the weight of the aircraft. Now we can say, at least under calm weather day where the wind velocity is 0 feet per second, we can then say that the velocity induced on the aircraft is equal to the velocity of the aircraft. So this induced velocity here is taken relative to the aircraft, as if our reference frame is now attached to the aircraft rather than some person standing on the landing field down there. So this is also equal and opposite to the velocity of the aircraft that we just saw calculated. And so we can say that that velocity of the aircraft is 172.3 feet per second. And now we want to take what's hopefully a very familiar equation for displacement as a function of velocity and time, and acceleration for that matter, that you've seen in your dynamics class. So let's lay out kind of our reference frame here. Let's say the start of the runway has an x position of 0 feet, an initial time of 0 seconds, and an initial velocity of 0 feet per second. This is really typical of an aircraft kind of leaving a runway, and very much in line with what you'd expect for a dynamic analysis. Now we know the runway length is 3,750 feet, and we just determined that the velocity required for takeoff is 172.3 feet per second, but now we need to figure out the time required for the acceleration to that velocity, and we also need to find the acceleration itself. So these middle equations right here, we can see x final minus x initial gives us the runway length. Time final minus time initial gives us the runway, the actual time to attain the required takeoff velocity under the acceleration that is of interest to us now, given the initial velocity of 0, and again the initial position of 0 and the initial time of 0. We now have enough information to determine accelerations and time. So let's start with our equation for x position. So x final is equal to x initial, which we saw as 0, velocity initial, which we saw as 0 as well. And from this, then, we can figure out the required runway, our required time under a certain acceleration to provide the takeoff velocity that was required. So let's solve this for t squared. We can say t squared is equal to 2 times x final divided by the acceleration of the aircraft. So this is one equation, two unknowns. That is to say, acceleration and time are unknowns. So now let's jump to this second equation here. Final velocity is a function of initial velocity, acceleration, and takeoff time, where we know initial velocity was equal to 0. So from this equation, we can say time is equal to final velocity divided by acceleration. And then we can say that time squared is equal to velocity final squared divided by acceleration squared. So just to give a little perspective on these equations, the equation on the left we could say is our x position as a function of time. So time and x position, this could be our t naught, our t final, and likewise this would be our x naught and our x final. And we would expect something of a parabolic displacement given the form of this equation right here. Frankly, just xf is equal to 1/2 acceleration times time squared. Likewise, for our velocity under constant acceleration, we would have the same t initial and our same, I guess I should use i's right there, and our same t final. And under this case, we'd also have our v initial set at 0 with our axis, and then v final. Here we've got our velocity in the x direction there, and we would expect this to be a linear increase, very much a slope-intercept equation right there. But now let's take our two equations and solve for the two unknowns that we were looking for. So we can just directly equate 2 times x final divided by acceleration is equal to velocity final squared times acceleration squared. So this then allows us to conclude that acceleration is equal to velocity final squared divided by 2 times x final. And so this then is our 172.3 feet per second that we saw from our lift force as a function of airstream velocity equation shown previously, divided by 2 times our runway length of 3,750 feet. And so this then gives us an acceleration of 3.96 feet per second squared is our acceleration here. Now this is very close to 4, so in later calculations I'm just going to round this up to 4 feet per second squared, but let's retain it for now and put that in our answers just for meticulousness in this state of the process. Now let's also solve for our takeoff time as a function of our recently determined takeoff velocity and acceleration. So here we've got t is equal to takeoff velocity, v final, over acceleration is equal to 172.3 feet per second divided by our 3.96 feet per second squared. And this gives us a takeoff time of 43.53 seconds as our time. Now at this point we can do a check and ascertain that our calculations are correct thus far. We can use this equation and say that x final is equal to 0 feet per second plus, 0 feet I should say, plus 0 feet per second times our time of 43.53 seconds. I know I could have just canceled these out right off the bat. I just want to give you a sense of where it all stands. Times 1/2 times 3.96 times 43.53 seconds squared, and this gives us a distance x final of 3,751.8 feet, which is pretty close to our runway length of 3,750 feet. And so this shows that our calculations are correct. Likewise, we can use this second equation. V final is equal to V initial of 0 feet per second plus our acceleration of 3.96 feet per second squared times our time of 43.53 seconds gives us a velocity final of 172.3 feet per second, and this is just corroborating what we saw earlier as our number for V1. So we've answered the first 3 parts of our 10-part exercise case study in the C-130 takeoff power requirements under maximum load conditions. Now let's move forward to our horizontal forces, our drag force, fuselage drag force, and required thrust force acting on the wings. This slide should look familiar from the part 1 portion of this exercise. Determining the forces acting on the aircraft, we'll start with the force of drag acting on the wing. Then we'll determine the force of drag acting on the fuselage. Then we'll use Newton's second law right here. Summation of forces in the x direction gives rise to our mass times acceleration. In this case, our acceleration, we're going to go with 4 feet per second squared, and our mass is going to be our 175,000 pound mass. And from that, then, we'll determine the thrust force required by our aircraft. We'll use that to get our V2, and we'll also use that to get our mass flow rate through all 4 propellers. But we'll touch down a little bit periodically to make sure we're all on the same page. So let's use our force of drag on the wing calculation is equal to drag coefficient on the wing times the dynamic pressure, 1/2 rho V1 squared, times our planform area. So this then gives us our drag coefficient of 0.03 times our, 1/2 times 0.0777 pound mass per cubic foot times our velocity of 172.3 feet per second, quantity squared, times our planform area of 1745 feet squared. This gives us a force of drag acting on the wing of 60,378 pound mass feet per second squared. And as usual, we have to do our unity conversion ratio, 1 pound force for every 32.2 pound mass feet per second squared. And so this gives us a force of drag acting on the wing of 1,875.1 pound force is equal to FdW. We'll put a box around that. Now for force of drag acting on the fuselage, we take the same equation, but in this case the drag force acting on the fuselage, or the drag coefficient acting on the fuselage, are 1/2 density of air velocity squared, and in this case our frontal area of the aircraft. So now we've got our drag coefficient of 0.02 for the fuselage times 1/2 times 0.0777 pound mass per cubic foot times our 172.3 feet per second quantity squared times our planform area of 225 square feet. And so this gives us a force of drag acting on the fuselage of 5,190.1 pound mass feet per second squared. And again, we keep note of our pound mass and distinguish those from pound force and recognize that our values have to come out in units of force, which we obtain by dividing by the unity conversion ratio of 32.2 pound mass feet per second squared for every pound force. And so this tells us the drag force acting on the fuselage at the moment before takeoff is equal to 161.2 pound force. Put a box around it, the next in our series of answers. Now we need to do something of a dynamic analysis where we can draw, in this case, the aircraft. And we know that the wings have a force of drag on the wings, FdW. We know the fuselage has a force of drag on the fuselage. We know that the propellers are providing a force of thrust, and we know that the aircraft itself has a mass of 175,000 pound mass, and it must accelerate at 4 feet per second that we saw previously. So we'll do a summation of forces. In this case, in the x direction, is equal to force of thrust. Force of thrust minus force of drag on the wings minus force of drag on the fuselage is equal to our mass times the acceleration. So let's carry that forward. This allows us to solve for force of thrust is equal to force of drag on the wing plus force of drag on the fuselage plus mass times acceleration is equal to 1,875.1 pound force of drag acting on the wings plus 161.2 pound force of drag acting on the fuselage plus 175,000 pound mass. Now note I'm using the mass of the aircraft, which is numerically identical to the force, the weight force of the aircraft, but in this case it's given in units of pound mass rather than pound force. And as I said earlier, for acceleration we're just going to round up to 4.0 pound force, or 0 feet per second squared. Now this expression right here, the mass times acceleration, gives us units of pound mass feet per second squared. We have to bring this back to our pound force using the unity conversion ratio of 32.2 pound mass feet per second squared for every 1 pound force of the aircraft. And so this then gives us, I'll break it down again, this gives us a total force of thrust required of the 1875.1 pound force plus the 161.2 pound force plus what we just calculated as 21,739.1 pound force to provide the acceleration required for the aircraft. So this then tells us we need a force of thrust coming from all four propellers of 23,777 pound force on the aircraft. Slightly rounded up in that case, but this then gives us some information of where to go next. So with that, we've got our wing drag force listed there, kind of rounded up. Fuel drag force, fuselage drag force, 161.2 pound force. And then our required thrust force, 23,775 pound force. Now we're going to move into the next steps of the process, the propeller air velocity V2 that manifests right at the instant of takeoff. So let me emphasize that these are at the takeoff velocity, takeoff velocity, takeoff velocity, takeoff velocity. Here we know that it's increasing in velocity as it accelerates from 0 feet per second to the full speed required for takeoff. So we're going to calculate our V2 now and then use that to calculate m.2, our mass flow rate through all four propellers required to provide the thrust needed to provide the acceleration needed to provide the upward lift force. We'll say to provide the velocity needed to provide the upward lift force needed for this aircraft. So let's return to our diagram. In this case, of all the forces acting on the aircraft, we found our aircraft velocity of 172.3 feet per second, which induces the wind speed on the aircraft at the takeoff condition. And now we're looking for the V2, the velocity of air exiting the propeller right here, and thus providing the thrust, the velocity needed, the differential of which provides the thrust needed for the aircraft itself. So let's zoom in. Let's move our control volume from surrounding the entire aircraft to surrounding, we'll just say, looking at a profile of all four engines at once. So again, these are engines that we'll say are equally dividing the load, but we can look at all four at once and figure out the velocity 2 that we need to provide the thrust and the corresponding mass flow rate. So we just saw that we calculated the thrust force required to accelerate this heavily loaded aircraft at 4 feet per second squared. And now we're going to delve into this equation and use that to calculate what we need for V2 to begin with. So let's kind of take this force of thrust is equal to mass flow rate, F2, force of thrust is equal to m.2 times V, get a good dot there, V2 minus V1, and we saw that m.2 is equal to density area V2 times V2 minus V1. You may recall we can't use V1 for our mass flow rate, as was exemplified in case study part 1 of this series. So here we've got V2 squared minus V1, V2 is equal to the force of thrust. So we can solve this equation for V2 squared minus V1 V2 minus force of thrust divided by density times area is equal to 0. And we see that that is of the form ax squared plus bx plus c is equal to 0, which lends itself to use of the quadratic equation. So now we can plug in values for these. We can say we're solving for v2, that is our stand-in for x in this case. So v2 squared minus 172.3 feet per second, that is our v1, our velocity at takeoff of the aircraft itself. Then we've got times v2 minus our 23,775 pound force, times our unity conversion ratio of 32.2 pound mass feet per second squared for every 1 pound force. Put that right there. Divided by our density of 0.0777 pound mass per cubic foot, times our 4 engines, each of which has a swept area of pi fourths times 13.5 feet squared. So this then gives us a little more compact representation of v2 squared minus 172.3 feet per second, v2 minus 17,208.6 feet squared per second squared. And keeping in mind, if we didn't use this unity conversion ratio right here, we would have different units, and we have to have dimensional homogeneity in our equations. That is to say, every term in this expression has to have units of feet squared per second squared, otherwise our answer is junk. So let's say now this is hopefully going to activate. Okay, this is equal to 0. So now let's solve for v2. We can use the quadratic equation. v2 is equal to 172.3 plus or minus the square root of 172.3 squared minus 4 times a, which happens to be 1 in this case, times negative 17,208.6 feet squared per second squared, all over 2a, which is 2 times 1. So this then gives us the final form of 172.3 feet per second plus or minus the square root of the expression shown there, which was 313.88 feet per second, all over 2. And we know it's unrealistic to do 172.3 minus 313.88. That would give us a negative velocity. So when we work through the calculations, we can then say that V2 is equal to 243.1 feet per second. We'll put a box around that right there. And likewise, m dot 2, maybe I'll jump to the next slide. So now with V2 listed, we can then calculate m dot 2 is equal to density, propeller area, total propeller area, and then times our velocity 2. So this then gives us our 0.0777 pound mass per cubic foot, times our propeller area, 4 propellers, times pi fourths, times 13.5 feet of diameter for every propeller, and then times our velocity of 243.1 feet per second. And so this then gives us a mass flow rate of 10,814.9 pound mass per second is equal to m dot 2. Put a box around it, substantial step in the process. And now we want to just kind of check our force of thrust equation. So let's do a thrust check. It's always good to kind of second check your calculations when you're working through these processes. We've got our force of thrust is equal to m dot 2 v2 minus v1. And so if we plug in our values here, we've got our mass flow rate of 10,814.9 pound mass per second times our differential velocity of 243.1 feet per second for our propeller exit velocity, and then 172.3 feet per second for our propeller inlet velocity. And this gives us a force of thrust of 765,695 pound mass feet per second squared, which we know is not units of pound force. So we'll take our 765,695 pound mass feet per second squared, and we'll recognize that 1 pound force divided by 32.2 pound mass feet per second squared is equal to 23,779.3 pound force is equal to our verified force of thrust. So 23,780 is essentially what we're looking for. And when we look back at this, we just calculated 23,780. And previously, through the summation of forces is equal to mass times acceleration, we calculated 23,775. So we just did the use of the momentum equation, and we got 23,780 pound force, which is in good agreement with what we see here, just a check of the calculations. Likewise, we saw the propeller downstream velocity is 243.1 feet per second, and then the total mass flow rate through the propellers is 10,815. So we use this to verify the thrust equation, and we used Newton's second law to calculate thrust. And so we landed in the same spot, and we've got good consistent results across the board. Now let's move forward to calculate the total propeller power, propeller fluid power first, required to keep this to provide the acceleration of 4 feet per second squared on this aircraft. So we'll start off with just the power form of the general energy equation, this big equation shown right here. And we also have our mass flow rate, which we just calculated before. And now we want to figure out what terms can remain and what terms can disappear. So while we call this a turboprop engine, it's actually regarded as a pump or like a compressor or a fan, something that energizes the flow with respect to our reference frame. So we're going to say there's not a turbine present in this analysis, and we're going to say the mechanical losses are negligible. And then we're also going to recognize that everything's at sea level on a horizontal airfield. So we're just going to say Z1 is equal to Z2 is equal to 0 feet. So this GZ1 term will cancel with GZ2 term right here. Likewise, we're going to say everything's at atmospheric pressure for the control volume that we draw around our engine. So P, pressure over density 1, is equal to pressure over density 2, which is our instance in this case as well. And then all we really have to do is solve for our pumping power in terms of our differential velocities, where we just finished calculating V2, the propeller exit velocity, and earlier from the lift and weight forces, we were able to calculate the takeoff velocity required for this aircraft. So we're looking at the power required by the engine at the instant it leaves the runway that it's taking off from. So again, looking closer, taking our control volume right here, we have our velocities given. We have our pressure term disappears, our gravitational term disappears, gravitation and pressure right there. There's no turbine, no mechanical losses. So we have an expression for power of the pump, that is to say all four engines, because we're still looking at the aircraft as a whole. Later, we're going to subdivide it and determine the individual shaft power of the engines. But using this information and the power form of the general energy equation, we now have an expression. In this case, I'll just say this simplifies to W dot of the pump is equal to M dot 2, which we've seen earlier, times V2 squared minus V1 squared over 2, all coming from the power form of the general energy equation. So let's plug in our values here. So power of all four pumps, that is to say all four engines working as fluid devices, not quite as shaft power yet, is equal to mass flow rate times our downstream velocity, or our propeller air velocity, minus our upstream velocity, the induced wind speed on the aircraft as a whole. And so this allows us to make use of our mass flow rate, M.2, 10,814.9 pound mass per second, times our differential kinetic energy on a specific basis, so 243.1 feet per second, quantity squared minus 172.3 feet per second, quantity squared divided by 2. And so this then gives us a power of the engine. I think I should just write it over here. So W dot pumps, all four engines, I should say, is equal to 159,034,835 pound mass feet squared per second cubed. Now, you may recall from fluid mechanics that these are the dimensions of power, but it's not the units of power that we're looking for. So first we've got to do our unity conversion ratio. So 1 pound force divided by 32.2 pound mass feet per second squared. And this then gives us 4,938,970 pound force feet per second. Now that's also a unit of power, but it's not the common unit of power used, at least in this case, by aircraft engines and listed in all the data sheets that I've found for this C-130 aircraft. So let's take our 4.9 million, I'll keep all the numbers right here, 970 pound force feet per second, and multiply by our conversion from those units to horsepower. So there's 550 pound force feet per second for every 1 horsepower. And so this then gives us 8,979.5 horsepower. For all four engines. And so this, put right here as our power of the pump. It's not actually the final step of the process. On the one hand, we can calculate the fluid power per engine, WP, E, is equal to, we'll say, power of the pumps, all four pumps, divided by N, we'll just say is the number of pumps. So this then gives us our 8,979, frankly, I could just round that up to 80, horsepower for all four engines divided by 4 engines. And so this gives us then 22,045 horsepower per engine. as the fluid power of the engines. So this is the fluid power provided by the propeller blades, not the power provided by the shaft to the propeller blades. That's in this case, we'll say shaft power per engine is equal to the power of the pumps themselves per engine divided by the efficiency of the propellers. And in this case, we've got our 2245 horsepower per divided by our 50% efficiency of those engines. And so this gives us 4,490, that is to say 4,490 shaft horsepower per engine, as equal to W S comma E. So this is one of the answers that is actually expected in the boxes. I guess I could kind of get rid of these so I'm not misleading you. This is what we'll list as the power of the engine. And this actually comes really close to the nominal value listed in the C-130 information for the power of those engines. Now for our last step, it behooves us in a sense to recognize, on the one hand, we've got our propeller fluid power, then we've got our shaft, and then we've got our turbine, and the turbine is receiving fuel. So we'll say volume flow rate of fuel times energy of the fuel. That's sending chemical energy into the engine. So we initially calculated the fluid power provided by the engines themselves. So this was our W dot P comma E. Then we divided by the propeller efficiency to get our W dot S comma E. And now we're dividing by the engine efficiency of 30% to get, I'm going to say it's W fuel comma E. This is a little misleading. I should actually use E for chemical energy rather than work, but just so I don't get you too confused with terms, we're going to say it's using the fuel energy drawn directly from the shaft energy and the engine efficiency. So maybe I will make this into an E just to clarify that it's energy, it's not work. Our energy flow rate, it's not work rate. So let us take here, I'll just use kind of the notation I had previously. So we'll just say energy of the fuel per engine, energy flow rate of the fuel per engine is equal to work of the fuel per engine, which is equal to power of the shaft per engine divided by the efficiency of the engine. So this is our 4,490 shaft horsepower divided by our efficiency of 30%. And this then gives us 14,967 horsepower of fuel for our engine. So this represents chemical power. That is contained within the fuel itself, and it's not really convenient to work in terms of chemical power using the terms we have right there. So let's convert it into British thermal units per second using some of the many conversions we've seen already. So on the one hand, we'll just take our chemical energy flow rate, so this has units of power, is equal to 14,967 horsepower. And then let's multiply by our conversion of BTUs per second, or we'll convert that into BTUs per second, so 0.7068 BTU per second for every 1 horsepower. And so this gives us 10,578 BTUs per second. And this is for every engine. This is the chemical energy flow rate into the engine in units of British thermal units per second. And then to get the total fuel power going into the engine, we're just going to take the number of engines times the fuel power per engine. Engine. And so this is 4 engines times 10,578 BTUs per second per engine. And so this then gives us 42,314 BTUs per second of chemical power going into the aircraft, chemical power of the JP-8 fuel. So all 4 engines, this is the power leaving the fuel tanks, providing the acceleration needed for this aircraft to take off the ground. Now, in order to determine the amount of energy in the fuel itself, we need to multiply the energy flow rate, E dot, so notice the absence of a dot gives us energy, times the time required to take off. So this then is our 42,314 British thermal units per second times what we saw way earlier as our takeoff time of 43.53 seconds of takeoff time. And so this gives us 1.841 million 918 British thermal units of energy is equal to the energy of the fuel, and I'm going to say this is chemical energy. Now that energy is equal to, the volume flow rate, or the total volume. We could say the volume flow rate times the power of the engine times the time, but we could also say it's just the total volume used times the energy content of that fuel. So from that, we can calculate the volume of the fuel used for takeoff is equal to the energy of the fuel for takeoff divided by the time required, divided by the energy content of the fuel. So this would just be our little fuel right there. This is just volume flow rate in gallons. This was volume flow rate in gallons per second. We don't want to use this equation as we did in case study 1 because we can just use this equation. So this then is our 1,841,918 BTUs divided by our fuel energy content of 135,000 British thermal units per gallon. And this then gives us 13.64 gallons of fuel is the volume needed just for the takeoff. That is to say, for 43.53 seconds of fuel use at an acceleration of 4 feet per second squared. So let's carry this forward into our final table here. And we can recall that we worked through sets of calculations. So the first set was get the takeoff velocity needed by the aircraft to provide a lift force that's equal and opposite to the total weight of the aircraft. Provide an acceleration of 3.96 feet per second squared. For subsequent calculations, we just rounded this up to 4 feet per second squared. We found the takeoff time from an initial velocity of 0 feet per second to an aircraft velocity of 172.3 feet per second was 43.53 seconds. We saw that at 172.3 feet per second, right before takeoff, the wings have a drag force of 1,875 pound force. The fuselage experiences a drag force of 161.2 pound force. And for these forces to be overcome and produce an acceleration of 4 feet per second, we need 23,775 pound force of thrust to overcome both these drag forces and provide this acceleration. Using that thrust force, we were able to calculate the velocity of the air downstream of the propellers for each of the 4 engines. From that, we were able to calculate the mass flow rate through each of the 4 engines, through the swept area of each of the 4 propeller blades. And then using these, we were able to double check our results and verify that indeed we get the right thrust force. Then using the power form of the general energy equation, we were able to get the power of all 4 engines acting really by superimposing a control volume across the whole thing. And then we divided that by the propeller efficiency to get the total engine horsepower. Then we divided by the number of engines, which was 4, and we got our 4,500 horsepower for each of the 4 engines there. Then we had to further divide that power by the engine efficiency to get the chemical power, which I listed as E dot sub F, chemical power of the fuel going into each of the 4 engines. We then multiplied those by 4 again to get the total fuel power. So we could say the total fuel power. And then we multiplied by the takeoff time and use that to get the volume and the volume flow rate, this 13.64 gallons of fuel used for takeoff. So earlier in part 1, we saw that the engines were only around 2,200 horsepower to maintain steady flight at constant elevation, but we realized that that was insufficient for takeoff power. But in this case, we looked at the actual operational conditions of a fully loaded aircraft for wartime conditions, and we were able to conclude that the engines have to be about 4,500 horsepower, that is to say shaft horsepower, to give it a full runway takeoff. Thank you.